Welcome back to the Valve Studio. I am playing with vacuum tubes again. It's taken me quite some time to get back to the bench, but I have a project in mind where I want to build an amplifier with these metal cans. I have a bunch of these 6SJ7s, and I want to find out how much I can do with just using these to build a guitar amplifier. So I'm going to use a Fender Reverb transformer here, which is designed for an 8 ohm load that gives a reflected impedance back onto the Pentode or the plate of whatever's driving this at 22K. And I'd like it to run off of batteries. So I purchased one of these. This is a 225 volt 20 watt DC to DC converter. So I should be able to get up to 225 volts with this, and using this not only as the preamp tube but as the power amp tube. And then I have another one here. This one here is for my filament supply. This is a step down DC to DC converter that'll go from up to 28 volts input and go down to my 6.3 for the filament on this tube here. So I have some challenges in the design portion of it because the data sheet gives some recommended values for voltages and currents, but I'm nowhere near any of that. So what I'm going to show you is I was using Spice to do some optimization of that, and that was a little bit tedious. So I came up with this tool called the Pentode Class A1 Designer, which is a Python program that lets you vary all the parameters, the plate voltage, the screen voltage, the load impedance, and the bias current. You can vary all those in a very interactive, very fast interface to pick your starting point to do design work if you're making a Class A1 amplifier, which is Pentode's. So let's get started. All right, let's first look at the General Electric data sheet for the 6SJ7, which is the tubes I'm looking at today. The plate dissipation is 2.5 watts. The screen dissipation is 0.7. And these are typically used as preamp or small signal amplifiers. Here's a Class A1 amplifier. So they show you the screen voltage, and they show you the plate voltage, and these are recommended values. This is the from the General Electric engineers figured out that this is a kind of an optimal setup. So in my situation, I could use this voltage here, 100 volts, and for both of these because I only have 225 volts to work with. But that and that will work fine for the preamp tube, but the power amp tube, I'd like to kick that up a notch. So let's continue looking down the some data sheets here. Here is the plate dissipation or the plate characteristics for changing the screen voltage. So you hold everything constant, but you change the screen voltage. So this is one of the typical plate characteristics. Here's the other one where you hold the screen voltage constant and you change the grid voltage. That's what this says here. EC2 is the screen voltage, and they're changing the grid voltage in increments of half a volt all the way down to -7. So this is the line you typically the graph you typically put your load line on. And since they chose 100, this upper trace here, right here, is the equivalent of this one right here on the graph above. So that's typically the correlation between this graph and this graph, and we can run this plate screen voltage anywhere we want. All that does is it either expands or contracts all the curves over here. And if we go down, we see these are the triode characteristics. Here's the transfer characteristics here. So, all right. But what we're focusing on today is we're going to look at this thing here. And the way we're going to do that is we're going to use NGSpice, which is a version of Spice that is a little bit more interactive than Spice 3 from Berkeley. And in order to run Spice, we need a tube model. So I found some tube models that look like they're pretty accurate by this gentleman here, this Ayumi. And I found several of them that have the same sub-circuit definition, where you have the anode, the screen, the grid, and the cathode. Okay, so let's look at the Spice definition file here. This is the circuit definition file, so we include that model. We have 3 power supplies connected up, voltage sources, the grid, the screen, and the plate. And then here's where we're going to run our simulation. We're going to run a DC simulation from 5 to 600 volts on the plate, and we're going to vary the grid voltage from down to minus 15. So I'm going to go ahead and run this thing here. We'll go ahead and show you. This is what that with the settings that I have in the circuit definition file. We're basically replicating this curve here, this characteristic here. Well, in fact, let me make a change over here. Let me change that step. We change that step definition from 1 to half a volt so we can get a more accurate representation. All right, so this graph here coming out of NGSpice is the equivalent to this characteristic here. So if we had a 100K load across here, where this would be our load line. This is our power dissipation limit here. So from this we can pick the bias point that we want to pick, and we can move the load line around and basically kind of get what we want out of this. But the variables that we can change at this point as being designers, we can move the load line up and down, which is changing the bias current. We can move the bias voltage forward and back across the voltage sweep. We can change the angle of this by changing the load line, and we can also change the screen current, which will either compress or expand these series of red curves. And you can use Spice for this, but let's say we wanted to change one of those things. Let's say we wanted to use a 250K resistor instead of this 100K. So we would come over here to our and change 100K right here to 250, and run this again. And here's what a 250 ohm resistor would look like. 250K would look like from a load perspective. Okay, so editing the file, rerunning Spice, it gets tedious because you have 5 variables that you want to tweak, and to go back and forth, we need to optimize that. Right now, this is set up for a preamp tube to run as the first stage. But running it as power tube is a little different situation. So let me show you what I came up with for this. I came up with this thing called the Pentode Class A1 Designer. And what it is a Python Qt5 application that runs NGSpice in the background and generates these this plate characteristic, as well as putting the power dissipation and the load lines on here. So let's go. We can choose between a lot of different Pentode tubes with this tool. Here's 6SJ7, which is what we're talking about today. All right, so we got to get our load lines equivalent here. All right, so we have a 100K load here. And these plots here are actually plotting the output from NGSpice. So whenever anything changes here, it goes out and reruns NGSpice, gets the results, and plots them back up on the screen. So let's look at, if we were to use the SJ7 for a power output tube, let's look at the thing on the data sheet here that's important for us to know is the plate dissipation limit here is 2.5 watts. So, theoretically we might be able to get maybe half of that out. So let's see if we can do that with this tool. So our supply voltage is 225 volts. All right. And that with an 8 ohm speaker connected to that Fender reverb transformer, the reflected impedance that the plate sees is 22K. All right, so this is what our load line is now looking like. The green line is 8 ohms. Purple line here is 4 ohms, and the blue line is 16 ohms. So we need to, in order to maximize the output power of this, we need to maximize the voltage swing, which is this swing here. And we also need to maximize the current swing, which is in this direction here. So we need to move our load line around. To move it, we can move the bias point back and forth with voltage. We can move it this way with the voltage slider, or this way. But in our case, we have to set it to 225. You can come in here and type in the value here. So the X direction for the voltage is set by our power supply. We can move the bias point up and down as well. And we'll move up here, and now we're off the screen here. All right. So in order to change the scale over here with this auto scale on, we've got to change the screen voltage. All right. So I'm going to drag this up a little bit to get it to rescale. And then I want to show you the effect of the screen voltage on these curves here. Now, as we move these sliders, NGSpice is getting called for every time the value of the slider changes. So every time this moves up and moves at all, it's rerunning NGSpice and getting the values and then coming and plotting them in this tool. So we can choose a screen voltage anywhere we want, which affects where the load line is placed on the plate characteristics. All right, so let's say we choose 10 milliamps for our bias point current. And then we we want this intersection here to be right below the knee. All right. So our excursion on the green goes from about 20 milliamps down to 0. That's 20 milliamp swing. And it swings from, let's say this is about 25 volts up to 450 volts. So there's another feature of this tool that what you can do is you can click here and drag your mouse down to here. And this little results portion right here shows you the delta V, which is 459 minus 25. The delta V is 433 volts. And the delta current was 19 minus 0, which is 19 milliamps. And that works out to be 1.1 watts. So if we bias this up at 10 milliamps of current, we're gonna be underneath the power dissipation for the plate, and our voltage, our grid voltage at this bias point. This is 0 up here. This is 1, -2, -3, -4, about -4.25. So that lets us pick the resistor that we're going to use in the cathode bias resistor. Now we have to check the screen dissipation. So the screen currents are also plotted on here as well from the NGSpice output. So this is 0, 1, 2, 3, 4, but right about in here. So that current over here is about 2 milliamps. For the screen current at 225 volts. So screen current, what did I say? 225 volts at 2 milliamps. What did I say? About 2.5 milliamps is 0.5 watts. So we're below this 0.7 watts here. All right, so this Pentode designer allows you to change the bias point. The bias point, which will move your load line up and down. It'll allow you to change your supply voltage back and forth. It'll allow you to change your load, and most importantly, it'll allow you to change your screen voltage. So you can change all the variables all at once with this tool, and this will give you a good starting point for using a Pentode for a Class A1 amplifier. All right, well, there you have it. Using 2 of these, a reverb transformer, and 2 DC to DC converters. I'm about to take on a project and figure out if I can build a guitar amplifier with just 2 tubes of the same type. All right, thanks for watching.